Thank you all for tuning into my talk today. This talk will be my Goldschmidt Medal presentation, so please let me start with a few words of thanks to all those who played a role in presenting me with this amazing honor. First off, I'd like to thank the Geochemical Society for the great job they do in supporting and advancing the field of geochemistry. I'm particularly indebted to my nominators, Al Hoffman, Stan Hart, Alex Halliday, and Bernie Wood, who are all people that have been my heroes in this field for a very long time. I find it particularly humbling that this group would consider me worthy of this award. My graduate training was in the heyday of Apollo and the growth of the field of cosmic chemistry that fueled. My PhD advisors, Doug McDougall and Gunter Lugmer, gave me a lot of freedom to pursue my own interests, but they also opened the window to the topics that would fascinate me then and for the rest of my career. Gunter further taught me how mass spectrometers really work, and an education that was further enhanced by Lou Brown when I moved to Carnegie. At Carnegie, George Wetherell and then Sean Solomon built up a geochemistry, cosmic chemistry group that at various times has included Typhoon Lee, Fuad Terra, Steve Shirey, Julie Morris, Eric Howery, Connell Alexander, and Larry Nittler. Working with and, well, frankly, just being around this group for the last few decades has been an amazing experience and for which I am most grateful. I'll take advantage of the virtual presentation here to list the many, though certainly not all the people that I've had the privilege of working with. I would like to offer my thanks to all of them for the scientific stimulation that was brought my way. I'm particularly proud, though I claim no credit, in how many of the postdocs I've worked with that are either already or well on their way to leadership positions in the field of geochemistry. Of course, nothing that I've done would have been possible without the funding provided by Carnegie, by the National Science Foundation, and by NASA. Finally, I'd like to acknowledge and thank my wife of 22 years, Sonia Esperanza, for all the aspects of my life that she's contributed to. This selfie at the bottom of the slide was taken on the top of Haleakala volcano in Maui a few years ago, and we were very much hoping to be at the same place the week before Goldschmidt this year, but a few microns of RNA had other plans for all of us. Moving on to my science presentation today, I'd like to examine which aspects of the modern Earth may relate to processes that occurred during or soon after Earth formation. The work I'll be talking about was done in collaboration with others, in this case with those shown on this slide. I particularly want to thank Jonathan O'Neill and Jesse Rymick for organizing field seasons in remote areas where he saw amazing geology, but also returned alive and unharmed. My special thanks go to Maud Boyer, who during her postdoc at DTM showed that there was still exciting new information to be extracted from the then mature samarium-neodymium system, the search for which has kept us both busy for the last 15 years. The 1970s, when I was a student, was a time when the geochemical community was building the case that the primary process responsible for chemical differentiation of Earth's interior was the extraction of continental crust. A very simplified representation of that model is shown on the right. It starts with primitive mantle of a composition equal to the bulk silicate Earth. From the primitive mantle, a small mass fraction of continental crust is extracted, but because the continental crust is so enriched in the highly incompatible elements, a good volume of residual mantle is created that's depleted in those same elements. And it's this depleted mantle that then serves as the source of global mid-ocean ridge basalt volcanism. The consequences of the model for a number of trace elements is illustrated on the left, and while not all elements in this model fit perfectly, as shown by the bumps and wiggles in the brown pattern that shows the combination of continental crust plus morb source, at least in the general aspects, the model is almost certainly correct. What I'd like to explore today, however, is whether this process is the only or even the primary cause of mantle differentiation. If one turns to the radiogenic isotope data from morb and continental crust, model ages for the development of their chemical complementarity range widely, but they tend to give ages around half the age of the Earth. Now, these ages almost certainly do not reflect discrete events of crust production, but they're instead more likely something like, well, an average age for a process that has continued throughout most of Earth history. What is surprising here, though, is that Earth formation almost certainly was accompanied by a vast array of energy sources that should have effectively driven differentiation of Earth's interior. Yet the signature of that early differentiation on Earth is difficult to see, especially in comparison to the data for Mars and the Moon, where these early differentiation events dominate the history of their interiors. Perhaps the early differentiation on Earth was erased by effective mixing driven by mantle convection, but perhaps the long-running process of continent extraction is only built upon compositional signals that were, in fact, established during or shortly following Earth formation. To investigate the role of earlier differentiation events, we've combined two approaches. First is a focus only on Earth's oldest crustal rocks. And second is to study the short-lived radioisotopic systems in these rocks, particularly the decay of 146 samarium to 142 neodymium. The ancient rocks of the continental crust preserve a picture of early Earth conditions, but one that's often overprinted by later metamorphism. The short-lived radioisotope systems provide the opportunity to see past these later metamorphic events because isotopic variability in the daughter element is created only while the parent isotope is alive. This is illustrated schematically in the diagram on the right. The colored circles here represent differentiation events. When they occur before the parent has decayed away, in the light gray shaded area, for example, they can create complementary differentiated reservoirs that evolve to measurable differences in daughter isotopic compositions, like in the green and the blue cases shown in the diagram here. At some point in time, however, the parent isotope has become so low in abundance that changes to parent-daughter ratio no longer can lead to measurable changes to the daughter's isotopic composition, such as in the yellow, orange, and red points here. For the samarium neodymium system, which has a half-life of about 100 million years, this cutoff occurred about 4 billion years ago. What this means is that if rocks display a range in 144 neodymium, that isotopic variability must reflect a chemical differentiation event that occurred prior to 4 billion years ago. Looking first at the locality where variability in 142 neodymium was first reported by Harper and Jacobson in 1992, this is the Eoarchean rocks of southern Greenland. The majority of the samples have positive mu-142 neodymium, where a positive value indicates a source with superchondritic samarium neodymium ratio and hence incompatible element depletion. The signature is seen in both the mafic and felsic crustal rocks in the area, as well as the supercrustal rocks of the Garbenschiefer unit. The data shown in these figures, and most of those that follow, are summaries of literature data that are cited in our recent review paper in chemical geology. As you can see on the left-hand figure, the data show a fair range in 142 neodymium, but it's important to keep in mind that the measurement uncertainty on these points is on the order of plus or minus 5 mu units. So much of the observed variation may simply be analytical uncertainty, with the exception of the younger rocks that do show 142 neodymium closer to 0. The majority of the initial epsilon 143 neodymium isotopic composition for these rocks also is positive, consistent with genesis of these rocks from incompatible element-depleted sources. For 143 neodymium, where the measurement uncertainties are about the size of the points, the range in the data is real, but it has been the subject of much discussion through the ages about whether it reflects true compositional heterogeneity in the sources of these rocks, or instead is just an inaccurate calculation of initial epsilon 143 neodymium as a result of metamorphic changes to the samarium neodymium ratio well after these rocks were emplaced into the crust. Both the 142 and the 143 data, however, suggest that these rocks were derived from Hadean sources that had 147 samarium to 144 neodymium ratios between about 0.21 and 0.24, and these ratios are quite similar to the values calculated for the modern mid-ocean ridge basalt mantle. Hafnium isotope data provide less obvious evidence for incompatible and depleted sources for the Greenland rocks. Jeffrey Vord in particular, but among others, has made a strong case that the initial hafnium isotopic composition determined for zircons from felsic rocks provide a more robust estimate of their initial hafnium isotopic composition due to the relative insensitivity of zircon to later metamorphic changes to lutetium-hafnium ratio, in part because the zircons have very low lutetium-hafnium ratios to begin with. Nevertheless, the bulk of the data at least allow the contribution of sources close to that expected for the depleted mantle at that time, as shown by the line labeled DM on this plot. Furthermore, the initial hafnium data, particularly for zircon, seem to evolve down lines corresponding to 176 lutetium, 177 hafnium ratios of about 0.01 to 0.02, and these ratios are typical of those found in mafic to felsic crustal rocks. An important but often overlooked point about the use of zircon initial hafnium isotopic compositions in this context is that felsic rocks are not directly derived from melting of the mantle, but they're instead remelts of more mafic rocks that may predate the felsic magnetism by quite some time. The initial hafnium isotopic composition of the zircons in these rocks thus may provide a good estimate of mantle hafnium if the crustal prehistory of their sources is short, but it will plot to lower values of epsilon hafnium than the mantle if the crustal prehistory is along as even 100 to 200 million years. The neodymium isotope evidence for incompatible element-depleted sources for the Greenland Eoarchean rocks is also seen in similar age rocks from Labrador and Anshan, China, but other terrains, such as those in the northern Superior and the Slave Cratons, show evidence of derivation from incompatible element-enriched sources. On the left are the initial hafnium and 142 neodymium data for felsic rocks and their zircons from around the Nouveau Agatek supercrustal belt in the northern Superior province. The zircon initial hafnium data show evolution down trends consistent with sources having lutetium-hafnium ratios typical of mafic crustal rocks and with an age of about 4.3 billion years. Both this age and the inferred source lutetium-hafnium ratios overlap those determined for the mafic gneisses of the Nouveau Agatek supercrustal belt. A somewhat unique aspect of these data is that the younger felsic rocks in the area, including those with ages as young as 2,750 million years, show negative 142 neodymium, indicating that Hadean light rare earth element-enriched sources were involved in the genesis of felsic crust in this area for over 1 billion years. The oldest rocks of the Slave Craton, those in the Acasta region, show a similar story as the northern Superior Craton, with negative mu-142 neodymium and zircon initial epsilon hafnium data that trend with age down hafnium isotope evolution lines consistent with 4.2 to 4.3 billion year old mafic sources. The data for the Slave then diverge from this story at about 3.6 billion years by showing a strong shift towards less negative and eventually positive initial epsilon hafnium values, with mu-142 neodymium returning to near zero. The story in the Slave thus seems to be that the felsic crust formation involved a reworking of Hadean crust between about 4.2 to 3.6 billion years ago, but then it shifted to sources with isotopic compositions approaching those the depleted mantle would have had at that time. The mu-142 neodymium data for the Slave, however, never reached the positive values typical of the Eoarchean rocks of Greenland. As I mentioned at the outset, the variability in mu-142 neodymium in the rocks discussed so far testifies to the involvement of both incompatible element depleted and enriched sources for the most ancient preserved crust on Earth. The evidence is thus clear that continent formation did not begin from undifferentiated mantle, but from an Earth that was already significantly differentiated. When did this differentiation occur? Combining the data for the Eoarchean to Hadean crustal fragments where 142 neodymium data are available produces the plot that's shown on the left here. Although the data do not define a precise single differentiation age, the data do not allow this differentiation to have occurred much before 4.4 billion years ago. For example, the tie line between the Nouveau Agatek and the Iswa data here gives an age near 4.36 billion years. On the right on this slide is a beautiful piece of work by Lars Borg's group, who analyzed a wide range of lunar samples using modern techniques in the same samarium spike for all samples. As you can see, samples as diverse as Mare basalts, Crete basalts, and even mineral separates from the ancient North Acidic crust plot along single 146 samarium 142 neodymium isochron of 4.34 billion years in age. The interpretation given the lunar data is that it reflects differentiation of lunar crust and mantle in a single event, likely the crystallization of the lunar magma ocean. Later differentiation events on the Moon were insufficient to remove the signature of this initial differentiation. A different story is told by 142 neodymium for the Earth, where all the variability seen in Archean rocks, that's shown in the top left figure here, is reduced to barely, if at all, detectable values in modern mantle-derived magmas, that's shown in the bottom left panel. One can eliminate isotopic variability in these short-lived systems by mixing back together the chemically complementary reservoirs that were created during Hadean differentiation. The diminution of 142 neodymium variability in mantle-derived rocks through time is thus most easily explained through recycling of Earth's crust in the interior and the subsequent mixing of that material with its complementary chemical components in the mantle. This kind of model was pursued by Rosas and Cornaga in their 2018 EPSL paper, where they start with a very rapid crust production, shown here in the upper right figure, basically producing all of the continental crust at the time of Earth formation. And then they call upon a very high rate of crustal recycling that's balanced by a similar rate of crust production throughout Earth history, basically keeping the volume of continental crust constant through time. As shown in the bottom panel on the right, this type of model will produce mantle reservoirs characterized initially by positive mu-142 neodymium that diminishes through time as a result of the recycling and mixing in of this early formed crust. The topic I'd like to end with is the question of how much of the mantle has been affected by continent extraction. If continent extraction starts from a mantle with bulk silicate earth composition, the mass balance models that date back to the 1970s show that only a volume of mantle roughly equivalent to the upper mantle can be the depleted complement. This is because in order to reach the level of incompatible element depletion shown by the modern Morb source, for example the open squares in the diagram on the left, the volume of this depleted mantle must be relatively small. On the other hand, if the chemical consequences of continent formation are distributed across the whole mantle, then the amount of incompatible element depletion in the mantle will be relatively small. This would then require that the starting mantle was already incompatible element depleted before continent formation began. The 142 neodymium data that I've discussed here shows clearly that incompatible element depleted sources were formed during Earth's initial differentiation. We attribute this initial differentiation of Earth to the magma ocean episode caused by the moon-forming impact. In the Boye and Carlson science paper in 2005, in order to explain the difference in mu-142 neodymium between the modern Earth and the 20 ppm lower value in ordinary chondrites, we invoked the commonly invoked infamous hidden reservoir of incompatible element-rich material created in this initial differentiation. Removal of this enriched reservoir left behind most of the mantle with a moderate degree of incompatible element depletion, for example, as shown by the filled black symbols on the figure on the left. Now, with improved seismic imaging since 2005, this hidden reservoir, in fact, might not be so well hidden, as the large low shear velocity provinces, or LLSVPs, that are imaged in the lower mantle are now known to consist of compositionally distinct material, at least from the surrounding mantle. Although most, if not all, of the 142 neodymium offset of Earth from meteorites is now known to be due to nucleosynthetic differences, the magnitude of 142 neodymium variability caused by early Earth differentiation depends strongly on when that differentiation occurred. In our original paper, the differentiation had to occur before 4.53 billion years in order to create a 20 ppm excess in 142 neodymium in the depleted mantle. If this initial differentiation is delayed until, for example, 4.36 billion years, the depleted mantle produced in the event will evolve to a mu-142 neodymium only 4 ppm higher than the starting value, and this magnitude of a difference is not measurable given modern measurement precisions. So this last slide shows the results of the mass balance calculations in the model that we originally reported in our 2008 Phil Trans papers, but in this case it's recalculated on the assumption that the LLSVPs are the early formed incompatible element-rich reservoir. The depleted mantle complement to the LLSVPs is assumed in this case to constitute 95% of the mass of the mantle, and it's labeled EDM, or early depleted mantle. This model does a reasonable job of explaining the modern neodymium and hafnium isotopic composition of both DMM and the continental crust, but it fails pretty obviously for 207 lead. But this model is so sensitive to the lead concentration of average continental crust that if you raise the average crustal composition from the 11 ppm suggested by Rudnick and Gao to just 12 ppm, the lead isotopic compositions calculated for DMM or depleted Morb mantle in this model fall within the range seen in modern Morb. The main takeaways I'd like to leave you with are that we now have clear evidence that Earth's mantle was at least as chemically heterogeneous in the Eoarchean as it is today. This heterogeneity was generated by differentiation events that occurred around 4.4 billion years ago, likely driven by the giant impact that created the moon. Some portions of Earth's ancient crust were created by remelting of this Hadean mafic crust, whereas others were generated by melting a portion of the mantle that had a similar degree of incompatible element depletion as a source of modern mid-ocean ridge basalts. The isotopic consequences of this early differentiation were mixed away, at least for 142 neodymium, by the end of the Archean, and it's likely by extensive recycling of the early crust and mixing with its complementary depleted reservoirs in the mantle. The possibility exists that continental crust formation started not from a mantle of bulk silicate earth composition, but one that had already been depleted in incompatible elements during the differentiation driven by the moon-forming impact. If so, then it's likely that continent extraction affected most of the mantle, with the possibility that an early formed, incompatible element-enriched reservoir may have been isolated from mantle convection for most of Earth history, possibly sequestered in what are now imaged as large low shear velocity provinces at the base of the mantle. Thank you for listening.